So to return to the summary, which we have talked about a few times now, in electricity and magnetism, we've done Coulomb's law, Gauss's law. We've figured out the potential, the potential difference within an electric field. That's when you get potential differences when you have an electric field. Then we moved on to magnetism, where we had the Biot-Savart law, and then and Gauss's law for magnetism. So that's the top four red circled equations. And then I also reviewed that we have magnetic and electric force as well as the fields, and that's the Lorentz force. So what I want to do is to hone in on a couple things here. First of all is to recognize that Coulomb's law and Gauss's law in a lot of senses do the same thing for us. And Gauss's law is just a more generalized, a more generalized way of relating fields and charges. So we don't really, so in advanced E&M, we don't really need Coulomb's law. All we need is Gauss's law. Gauss's law encompasses Coulomb's law. It's just for us, Coulomb's law was easier to apply. And we're going to find the same thing with the Biot-Savart law, that we're going to replace that with what's called Amperes law. And the next thing we're going to do is Amperes law. So on the right-hand lower side here, I'm going to write down two things. I'm going to write down Amperes law and Faraday's law. You all already know what Faraday's law is, and you presumably know what Amperes law is because you've read the book. And those are the two laws that we're going to do that's going to add to this messy page. That pretty much is all of electricity and magnetism. And what I want to do is just to hone in a little bit on what's important here. First of all, you got the Lorentz force law. The Lorentz force law is independent. That's sort of important for the electric and magnetic force. But in terms of fields, what I was trying to say earlier is we've got Gauss's law. Gauss's law is going to be our general relationship between a field and charge. And then we got Gauss's law for magnetism. And we're going to, what we did for Biot-Savart law, Amperes law is going to do for us what Gauss's law did for us for electricity, replacing Coulomb's law. Amperes law is going to replace Biot-Savart law for calculating magnetic fields. So now I want you to just take a quick look at these four equations that I've circled in red now, red highlighter. Gauss's law is E dot dA and B dot dA. Notice that the potential difference, which doesn't have a name yet, is E dot dL. That is going to turn into Faraday's law. That is what we're going to start with in order to get to Faraday's law. So that is not Faraday's law, but it is going to be related to Faraday's law. And then, so what I want to do is just see what's really important about these equations, which these are equations that we're calling Maxwell's equations. What's really important about these four equations that are now circled in ugly red is the symmetry between the equations. And moving on to Amperes law, I just want to point out that we've got an E dot dA and a B dot dA. We've got an E dot dL, so now we want to talk about a B dot dL. So, for whatever reason, we want to know what B dot dL is. That's where we're going. What is Amperes law? Amperes law is a law that we're going to use to calculate magnetic fields from current distributions. Well, that's no different than what Biot-Savart law did for us. Savart law also calculated magnetic fields from current distributions. Also analogous to Gauss's law, right? Gauss's law, what did that do for us? It allowed us to calculate electric fields from charge distributions. Okay, so I got interrupted, so let me just, Amperes law is going to show us how to calculate magnetic fields from current distributions like Biot-Savart law, but it's a simpler form like Gauss's law compared to Coulomb's law. Gauss's law was for calculating electric field from charge distributions. Okay, so let's go ahead and see what Amperes law is. Amperes law tells us, and I'm not going to derive this, right? It's because this was figured out by Mr. Ampere, whoever Mr. Ampere is. Perhaps it was figured out by Mrs. Ampere, but Mr. Ampere got credit. Amperes law says that the integral of E dot dL equals mu naught I enclosed. Okay, let's talk about this. E dot dL integral and there is the little closed circle there. I'll explain that. In this case, the integral is over a line rather than Gauss's law, which was over an area. And so this is for a closed loop, right? A line is something like that. A loop is a closed line, not a clothesline, but a closed line. So you got, whoops, that was an arrow, line and a loop. So E dot dl over a closed loop equals a constant times the current enclosed in that loop. Very similar to Ampere's law, except it's a line integral instead of an area integral. It's an integral over a line instead of an integral over an area. And it says that the Ampere's law is magnetic field, not electric field. I hope that you all caught that. Magnetic field. Oh my gosh. Ampere's law is for magnetic fields. Magnetic field integrated over a closed loop equals mu naught times the current enclosed in that loop. Very similar to the way Gauss's law talks about. So we've got in Ampere's law, remember in Gauss's law, we had the Gaussian surface, right? And it's the charge that was enclosed by that Gaussian surface, right? This imaginary surface. In Ampere's law, we're going to have an Amperian loop. The Amperian loop is just this imaginary loop that we're integrating over and saying that the magnetic field has something to do with the current enclosed in that loop. So I say B dot dl, that is a dot product. It is two vectors. We are doing vector multiplication. So that's B dl cosine theta. B dl cosine theta, right? B dot dl is just B dl cosine theta. Okay, so why Ampere's law? Well, if we've got some arbitrary currents, right? I drew three arbitrary wires here, two straight wires and one wiggly wire. It doesn't matter. If you got some arbitrary currents, right? It just says, just like with the Gaussian surface, you just draw an arbitrary Gaussian surface. I'm going to draw an arbitrary loop. I'm just going to draw an arbitrary loop. It's a closed loop, and I know it's in 3 dimensions, but let's just pretend that all 3 of those currents go through the loop. Or you could even say 2 of the currents go through the loop and 1 doesn't. Doesn't matter. What we're saying is that if we integrate the magnetic field around this, the magnetic field around this imaginary loop, that the magnetic field is only due to the currents that pass through the loop. Right, the currents that pass through the loop. Let's just assume all 3 pass through the loop. If there's another current out here that doesn't pass through the loop, it does not contribute to the magnetic field about that loop. All right, so in practice, just like with Gauss's law, this can be a very difficult, it's a line integral. It's actually it's a line integral. It's a vector integral, right? So it's vector calculus, it's Calc 3. And so it can be very difficult to solve this in practice for arbitrary currents. But it makes it very easy to solve this for some symmetrical situations. Just like Gauss's law was good for point charges, line charges, and sheet charges, Ampere's law is good for some symmetrical situations. See how we can apply Ampere's law to the simplest symmetrical situation that we've come up with so far, which is a long straight wire. With this long straight wire, remember that we do understand the direction of the magnetic field, because notice that Ampere's law doesn't tell us anything about direction. It only tells us about magnitude, because B dot dl is a scalar product. So we do need to understand that the magnetic field goes around a wire, right, according to the right-hand rule. So we do need to understand the direction. So the magnetic field goes around that wire. Okay, so once we know that, and that the magnetic field, I guess the other thing we need to know, just like we needed to know with Gauss's law, that the electric field was constant at a constant distance away, we do need to understand that the magnetic field is constant at a distance r. It's dependent on r. So it's constant at a distance r away from the field, at anywhere around that loop. Okay, now we can apply Ampere's law. So Ampere's law says, let's just take an Amperian loop and put it around the wire. And let's make sure that the Amperian loop is symmetric to the magnetic field. Again, thinking back to the way we did Gauss's law, we always had to put a Gaussian surface that was symmetric in some way to the field. So let's just do an Amperian loop that has a radius capital R, an imaginary loop, and just put that around the wire. And then ask, what is the magnetic field at any point dl on that loop? So if this is dl, the magnetic field must point in what direction? Again, by the right-hand rule, it's hard to say which is behind the wire and which is in front of the wire, but in general, hopefully you can see that according to the right-hand rule, that the magnetic field is always going to be in the tangential direction on that imaginary Amperian loop. And notice that dl, the direction of dl, is also in the tangential direction, right? The direction of a line always points tangential to the line. So dl and b for this particular Amperian loop, right? This is the Amperian loop, the imaginary loop. It's not supposed to be not supposed to represent magnetic field or anything. It's just an imaginary loop that we put around the wire. That b and dl are in the same direction. That means that therefore, and I've changed colors by accident, b dot dl, the right-hand side, because b and dl are in the same direction, b dot dl, remember, is b dl cosine theta, and theta is equal to 0 degrees, so cosine of 0 is 1, so that's just integral of b dl. So we get rid of the dot product. You have to argue away the dot product. You can't just drop it. It's gotta come out mathematically. Left-hand side of the equation, right? And so, but the right-hand side, that still equals mu naught I enclosed. Okay, so first thing we did was we chose a loop so that b dot dl turned into bdl. The next thing is to recognize that the loop that we chose, magnetic field is constant at a constant radius r. So for the Amperian loop, so that was the first step, right, was the dot product. The second step is understanding that the magnetic field is constant so we can pull it out of the integral. But you have to know it's constant. If it's not constant, you can't take it out of the integral. Magnetic field is constant, so we take it out of the integral. I'm not going to write down what step 2 was, but step 2 was to recognize the magnetic field is constant over the Amperian loop so we can take it out of the integral. Step 3 is to do the integral. So now, step 3 in solving Ampere's law is to actually do the integral. And the integral is the integral around the line dl, which is a closed loop. So it's adding up all the little dl's. Look at your black loop there. It's adding up all the dl's that make up this loop. And so what is the integral of dl around a closed loop? If it's circular, that is then the circumference of the loop, and so we do the integral and we get 2 pi r, the circumference of the loop. And so you get b times 2 pi r equals mu naught I enclosed. Step 4, the final step, is to look at the right-hand side and ask how much current is enclosed by that loop. In this case, we've got a single wire, a single current going through the loop. So the amount of current enclosed is simply I. So step 4, again, I'm not going to write down in words what I'm doing, but I'm telling you, is to evaluate I enclosed. I enclosed is I. If you solve Ampere's law, you've got to do each of these steps every time. You got to deal with the dot product, step 1. You got to deal with the integral is making the integral doable, basically. In this case, recognizing b is constant and taking it out of the integral, step 2. Step 3 is doing the integral. And then step 4 is looking at the right-hand side and figuring out how much current is enclosed in that loop. That's what we got to do with Ampere's law every time. Okay, but there's not going to be many different examples, to be honest with you. There's not a lot of different examples. Right, so now we got to solve for b. I'm going to take this, instead of going to a new page and just write in the upper left, if I take step 4, b times 2 pi r equals mu naught I, and solve for b, therefore b is equal to mu naught I over 2 pi r. Check, right? That's what we found was the magnetic field. At a distance r from a wire, a long straight wire, we found using Beer-Savart law, doing an integral, that b is equal to mu naught I over 2 pi r. That is the magnetic field of a long straight wire calculated by Ampere's law. Now, how would this change if, for example, I had two wires going through the loop? What if I had a second wire going through the loop? Let's just say it's approximately, reasonably close to the other one, so I don't have to worry about the separation between the two. But if I have two wires going through the loop, both with current I, then how would that change this? Right? That would mean the I enclosed is equal to 2I. And so therefore, for the second version, it would be mu naught times 2I over 2 pi r, or mu naught I over pi r. Right? So, but you got to make sure that you're counting up all of the wires that pass through the loop, all of the currents in all of the wires that pass through the loop. That's Ampere's law applied to a straight wire. Last time I'll show you this messy picture. Now notice the symmetry that we've got. We've got two laws, B dot dA, E dot dA, and we got two laws, E dot dL and B dot dL. Ampere's law has a B dot dL in it. So there's some kind of symmetry going on here. We'll write these down more neatly next time.